Hello everyone, this is Dr. B. Surekha Reddy, Assistant Professor from Department of EC, Institute of Aeronautical Engineering, Dundigal, Hyderabad. So now I would like to start a course on digital system design, which is a basic course of electronics, communication and engineering branch. So I'd like to start with the today's topic of introduction to number systems. But before moving on to introduction to number systems, I'd like to give a brief overview about the course, the basic course outcomes, and the corresponding program outcomes which will be fulfilled in this particular, from this particular course. Okay. So, coming to the course overview. So here we'll be discussing about the fundamental concepts and basic building blocks of digital circuits. So here. Whatever the things we have at present in the daily real world is analog signals. So, but analog signals we have a bit of minute disadvantages are there compared to the digital world. So that's why every time we'll try to convert the particular analog signal into digital signal. So once we convert this particular analog signal into digital signal, we need to have a particular digital circuit in order to what is it? Realize that particular digital signal. Like, so for example, if I have a particular system over here, if there is a filter in this one, initially this might be any analog filter which filter out the basic things whichever we want from this particular analog signal initially. Okay, so the output also will be another analog signal only, but this analog signal, it is more prone to noisy conditions. So because of this reason, what we'll try to do is we'll try to convert this basic analog signal into digital signal by using different sampling and quantization methods. And once we convert this particular signal into digital signal, again what we require is again a filter. Anyhow, the information which can both the signals, that is this particular analog signal as well as the digital signal, both carries the same information. Information will be same in both the signals. So now whatever the filtering I want to do on this particular information, I need to pass it through this particular filter. So for this purpose, I need different types of digital filters and digital concepts, digital design concepts we require in order to work on this particular digital data. Okay, so basic fundamental concepts and the basic building blocks of a particular digital circuit will be discussed in this particular course. And next comes the number systems, designing of optimized combinational and sequential circuits, and memories. Here the memories will be only 1-bit memories over here. And next comes the programmable logic devices and the key concepts of hardware description language. So VHDL is basically, we have different types of programming languages such as C language is there. Previously C language is there, Java was there, MATLAB is there. So many different software programming languages are there. And VHDL also is the same such language which we will be writing basically on the digital circuits only. For example, here we'll be taking the consideration of OR gates, NOR gates, D flip-flops, and different type of logics pertaining to the digital circuits, and we'll write the code with respect to the digital logics. So that the basic idea of the VHDL overview will also be discussed in this particular course. And next comes the last one, that is the application in the area of VLSI design, microprocessors, microcontrollers, and as well as the embedded systems will be discussed in this particular course. So here the basic objectives of designing this particular course is here. At the end of the day, the students will try to learn how to simplify the logic functions using Boolean algebraic theorems and techniques. Implementation of conventional, combinational and sequential circuits. Basically combinational circuits, it doesn't have any clock in that one. That is, there won't be any synchronism with respect to the in between the inputs which we give or the output whichever we get. And sequential circuits basically will have some acknowledgement type of thing in asynchronous circuits and clock ticking in the sequential circuits. Next is the exploration of logic families and semiconductor memory. So once we learn about the digital circuits, we'll be more interested to work on the IC design technology, that is integrated circuit design technology. So once you look at the integrated circuit design technology, so what we'll be having is different logic families, how to design a digital circuit for a initially we'll be looking only at how to do multiplication, how to do addition type of things, but as we move on, we'll be moving on to the different type of functions over there, and how to realize those function, how to put those uh, functionality into the integrated circuits. So some explanation about different logic families and semiconductor memories will be discussed over here, such as PALs, PLAs, PROMs, EPROMs. All these things will be like the student will be able to learn. That is the basic objective of this one. And finally, the realization of micro and macro circuits using BHDL programming will also be learned in this particular course. So at the end of the course, the student will be able to get an outcome, that is the student will be able to outline the binary arithmetic operations and optimize boolean functions using Karnaugh and tabulation method. It's basically simplification. So if we have a very big equation, for example, f equals to, this is a function, like if I have some a b c plus a bar b bar c bar plus a b bar c plus a c bar b plus a bar b bar c bar, so on like this. I have more forms in this one. Okay, so now this entire thing can be minimized in terms of like 2 or 3 terms will be coming, or 4 or 5 terms will be there, and these many terms will not be there. Basically for simplification purpose, like whatever the binary arithmetic operations are there, we will be using different boolean functions, and the student will learn about the Karnaugh and tabulation methods in order to simplify this particular equations over here. So next outcome is make use of basic logic gates to realize the combinational logic circuits used in conventional electronic circuits. So basically about the OR gates, NOR gate, XOR gates, universal gates, that is NOR gate and NAND gate. All these gates will be learned in this particular course, and the student will be able to understand properly about this concepts, how to write a function. Like for example, if I have f equals to ABC is there, f equals to AB plus BC is there here. So here what we have is a multiplication, and here what we have is a multiplication, and between what we have is an addition over there. So for multiplication, what we'll use in this particular digital circuits is AND logic, and here plus is used for OR logic. Okay, so with the combination of this, like by using this basic logic gates, AND gate, OR gate, we'll be able to realize different type of combinational logic circuits used in the conventional electronic circuits. So next one is interpret the knowledge of flip-flops and latches in synchronous and asynchronous modules for memory storing applications. So now synchronous in the sense like with respect to the clock, how the particular inputs and output will be getting in synchronous with the clock, and asynchronous without the clock also, how we are going to get the outputs. All these things the student will be able to get an outcome of. Next one is the developing of Mealy-Murray models and state diagrams for the complex sequential circuit applications. So now Mealy-Murray machines are nothing but the algorithm. It's something like algorithm whichever we write in a particular programming language. So now if you look at the particular programming language here, in that particular programming language, what we'll do, we'll have a flowchart, we'll have a step-by-step procedure of that one. So that is to say, first start will be there, next followed by some input we'll be giving, and then again some logic will be there, whether it is true or false. Okay, and if it is met, then it's okay, otherwise it will again go back to the previous step. So like that it will be going on. Likewise in this Mealy-Murray machines also, depending upon the input stage and the present state, how the outputs will be varying, how we'll be getting the outputs, and how to look at those particular outputs, and how to prepare a proper VHDL code. All these things we'll be learning in this particular course. So next one is identify the different logic families memories, and programmable logic devices for understanding the architectural blocks of FPGA, that is Field Programmable Gate Array. So all these things will be coming across in the upcoming last modules, and there we'll be learning about like what are the digital families, what are the different memories such as a programmable and logic, programmable logic array, and PROM, programmable read-only memory. So all these things will be coming across, which are basically the basic building blocks of a field programmable gate array. So next is demonstrate the different modeling styles and data types in VHDL for implementing combinational and sequential circuits. So just in the case just like the case of a different programming languages, to write a particular code, we have different, like that is to say, to implement a particular logic or any application, we'll be having different type of methods. So those types are nothing but like modeling styles, and how the data types can be considered in this particular VHDL language will the student will be able to learn at the end of the course. So again, like course outcome 1, that is outline binary arithmetic operations and optimize Boolean functions using Cornag and tabulation method, comes under the Bloom's taxonomy level of understand. Next CO2, that is course outcome 2, will be coming under the apply level of the Bloom's taxonomy, and the rest of the things will be coming in the understand, apply and understand levels of the Bloom's taxonomy. So next comes like what are the program outcomes that will be fulfilled like based upon this particular course, that are PO1, that is program outcome 1, program outcome 2, program outcome 3, and program outcome 4, and program outcome 10. And also a program specific outcome, that is 2, will also be satisfied by you like with the help of this particular course. This course like PO1 pertains to the engineering knowledge, that is applying the knowledge of mathematics, science, engineering fundamentals and engineering specialization to the solution of complex engineering problems. And the proficiency of this particular program outcome will be assessed by ACE, that is external examinations, internal examinations and tech talks over there. So here, by using different concepts of mathematics, we'll be able to do the different do different problems in this particular digital system design course. And problem analysis is there everywhere in digital system design, and we can say it will be more for a problematic methodology only. Theory will be very less comparatively, and more problems will be there, and also more programming stuff will be there in digital system design subject over here. And next is design or development of solutions. So as we can see, there are different applications by using this digital system design. We can design new things, new technology, and these technology can be further used in the market also. And program outcome 4 is conduct investigations of complex problems, that is intense sequential circuits can be realized by Mealy-Murray machines. So those things can be accomplished here. And finally, program outcome 10, that is communication. So once we learn about this particular digital system design subject, we'll be confident enough to deliver a lecture on this particular topic, like whether it is a number systems or combinational circuits or sequential circuits or whatever it is, we'll be confident enough to give a seminar or a lecture or any presentation. Or even if we move on to the VLSI designing process also, like if it is a digital design, we'll be dealing with FPGAs mostly. So we'll be confident enough to deal with this particular FPGA designs, and we'll be confident enough to speak in a group of people. That is nothing but communicating effectively among our peers. Whenever we move out of this particular BTech course, then we'll be able to confidently discuss about this particular concepts among our colleagues in our office. So finally, program specific outcome 2 can also be satisfied by using this particular course, that is focus on the practical experience of ASIC prototype design, virtual instrumentation and SOCs. So among this, what will be fulfilled is SOC designs, that is system on chip designs. So system on chip designs is basically nothing but like we'll be taking the background as FPGAs we'll be taking initially, and on FPGA we'll be writing different circuits. We'll be putting the functionality of different circuits on this particular chips, and we'll be getting a system on chip design which will be used for a particular application. Okay, so these are nothing but the program course outcomes, program outcomes, and program specific outcomes that will be fulfilled by using this particular course. Next, let us see the syllabus of this particular course. That is, module 1 will be covering the logic simplification and combinational logic design. So here in this first module, we'll be covering the review of Boolean algebra and De Morgan's theorem. SOP, that is sum of product and product of sum, forms will be discussed. Canonical forms will be discussed. Carnot maps up to 6 variables. Binary codes, code conversion are discussed. Followed by second module, in which we'll be discussing about MSI devices here, in which we'll be having different types of comparators, multiplexers, encoders, decoders, subtractors, half and full adders, serial and parallel converters, and BCD adders, barrel shifter, and arithmetic logic unit, designs of this particular arithmetic logic unit. All these things will be discussed in module 2, followed by sequential logic design, that is the basic building blocks of a SR flip-flop, JK flip-flop, D flip-flop, master slave flip-flop, and different types of FSM circuits, algorithm, state machine charts, and pulse train generators, pseudo-random binary sequence generators, and clock generation circuits. All these things will be discussed in module 3, followed by module 4, that is logic families and semiconductor memories. So once we learn about the basics of digital system design, which consists of the combinational circuits and sequential circuits, we should be able to apply this particular functionality somewhere else. So that somewhere else will be nothing but the logic families, whichever we learn later on, that is transistor logic, NAND gates, and different types of semiconductor memories over there. And next comes the fourth module, in which we'll be discussing about VLSI design flow. VLSI design flow is very, very important when we start working on VHDL programming. So all these things will be discussed in this particular course. So these are some of the textbooks and the reference books which we can follow in order to perfectly learn this particular subject of digital system design. So let's start with the introduction to digital systems. That is, like, whenever we give any discrete inputs, then we'll be getting the discrete outputs. So, and even like the processing system also, it will be discrete information processing system only. And here the system states will be taken into consideration. So now, for example, in general, what we have is a analog data. Okay. So now in analog data, what happens is we have something like this one. This is a time varying signal here. This is amplitude over here. So in this one, for every point of time, we have a particular amplitude over here. So this is nothing but a continuous signal in which we have, it is continuous in time and as well as the continuous in amplitude. So if I say something is discrete, system input. So now over a period of n samples, what I'll be having is at particular point only I'll be getting one output. Okay. So likewise, at particular point only I'll be getting another output. And at particular one point I'll be getting one output. So like this, here it is 0. And likewise here, if I combine all these points, it will again look something like a sinusoidal signal only. So now here, this is a particular point. Again, this is a particular point. 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 Like this one, we'll be getting different sample points. So now once we combine these sample points, again we'll getting the same continuous signal only, but the difference is here, there won't be any output in these 2 points. Okay, there won't be any output in between these 2 points. Whereas in this continuous time signal here, you'll be getting the outputs at each and every 0.0001 at that particular seconds also, you'll be getting particular amplitude value. Whereas in discrete sense, what we'll be having is, it will be defined only from some known values. That is, for example, 0, 1, 2, 3, so on like this. Okay. So now whenever we give any particular discrete inputs to a discrete information processing system. So here it makes sense because here whenever we consider any particular system is there. Okay. So with respect to the input, we get the output. Okay. So now with respect to the excitation, the particular response will be there. So now this system is fixed. The system is fixed. With respect to the changes in the input, the system will also be making some changes, and correspondingly it gives some output. So likewise here in this particular digital system, if the input is discrete inputs, definitely the processing system also should be discrete information processing system only, because if you are giving any continuous information processing system, definitely the output also it will be considering only for some discrete information only, not for all the samples. So that's it. So for that purpose, what we need to consider is digital filters only. Again here, discrete information processing system example is a digital filter. Again, the digital filter has to be used here in order to process this particular discrete inputs, and as such with respect to this information processing system, we'll be getting a discrete outputs over here. So this is nothing but a digital system which consists of a discrete inputs, discrete information processing system, and it gives a discrete outputs. And here, while this processing is being going on, what will happen is it consists of different system states also. Okay, so now here this system states are nothing but what is the state of the system at present, what is the state of the system previously, what can be the state of the system in the future also, but basically we'll consider only previous states and the present states only, not the future states over here. So here what are the system states also. So once you process something, once you make some changes with respect to the input in this particular information processing system, that particular state will be stored here. And again, next time, whenever I get any new input, okay, sometimes we should be able to use the previous states also, previous states. That is what is stated in the sequential circuits. Basically, sequential circuits, it stores the memories over there. At least 1 bit memory will be stored over there. So that 1 bit memory, it will be storing of the past and as well as the present also in different variable manners. So that information will be again taken by the information processing system, and once it is done, again the corresponding values of at the present state will be given to the system state, which can be used in the next state also. So every time we'll be taking consideration into present state, next state. In that way only we'll represent whenever we write in a truth table for any state diagram, we'll consider it in the form of a present state and the next state over there. So here the system state says whether it is in the present state or the next state, and how to take the values from the from present state to the next state. All these things will be dealt with the particular system state over here. So I hope you understood. Like a digital system is basically, it consists of the discrete inputs, and it is processed by using a discrete information system, and the corresponding state of the system is shown by this particular system state. Here then depending upon the changes in the information processing system, we get a corresponding discrete output over here. So this is it here regarding the digital system block diagram or digital system basic blocks, whichever we have over here. So digital systems operate on discrete elements of information such as numbers, which are nothing but digits, or digital, that is like if we have any pocket calculator, we can take that into consideration, or letters which will be used in word processor, and pictures, that is in digital cameras. Pictures means like there will be having some pixel values over there, that can also be used as a digital system, system which will be operated in the particular discrete element. So any pocket calendar or word processor or any digital camera can be considered as a particular digital system. Okay, some systems use the continuous information also. For example, at present no one is using any continuous information processing system, whereas previously the people used to do that because we were more familiar with the continuous data only. So they were using older thermostats. Thermostats are basically used for calculating the temperature at any particular state and all. So next, in film cameras, instead of the digital cameras, people used to use film cameras, then take it out, then process it, and then some negatives will be getting, and from the negatives again they'll process the particular pictures. So it was very long procedure. But right now, as soon as you click the picture, then you'll be getting it. And every image, whichever we process using a digital camera, it will be consisting of different pixels in this one. All these pixels are nothing but again the digits or numbers. And slide ruler means like which is used to measure any particular thing, something like a scale over there. So nowadays no one is using that. What we are using is a digital scale only. So for example, which we can take is a common balance in a vegetable market. Previously, to weigh the vegetables, people used to use a common balance, that is known weights are put in this one, okay, on one side, unknown weights are put on the other side, and we used to weigh like with a half kg, 1 kg, or any 1/4 kg, or or anything else like that. But right now, even if it is like 1.252 or 1.054, even this type of kgs, or it can also be measured at present in the supermarkets or whichever the markets we can find. So most of the people are very much in this like interested in this particular type of digital system only, which weighs accurately. Even 0.05 grams also will not be, I mean kilograms will also be noted down, and particularly the price will not be modified. Okay, some of the vegetables might be extra for them, so there won't be any loss for the vegetable vendors also. Anyhow, so here that might be a loss for us anyhow. So here this is nothing but the digital data, whereas slide ruler, film cameras, older thermostats, it comes under some continuous information systems, and we can say these are obsolete. No one is using at present all these things. So digital systems majorly deals with the numbers. Everyone can see that we have digital cameras are there, digital computers are there, and now smartphones, smart computers are also there. That is different. But anyhow, letters also. Even in digital system, what we can do is like we can deal with A, B, C, D, and also small a, small b, small c, small d. All these things will be having its own value. Okay, so whenever I try to process any particular word, it will be having its own binary logic or hexadecimal logic or any other octal digit logic will be there in the number system. So all these things can be used to represent the discrete elements in a digital system. So digital systems consider discrete amounts of data. For example, 26 letters in the alphabet, 10 decimal digits. 26 alphabets means A to Z, capital, small a to small z, small, and decimal numbers is 0 to 9. It is not 1 to 10. It is not 1 to 2. Rather than it is 0 to 9 only, because 10 it consists of two numbers, 1 and 0. That's why every time, like whenever we take any decimal digits or any numbers, like what we'll start considering from is 0. We'll consider it from 0. So 0 to 9 decimal digits and 26 letters of the alphabets can be considered the examples of discrete amounts of data in the digital system. And the larger quantities can be built from discrete values, that is words made of letters. Okay, so now if there is any very larger values are there, then each word will be having different types of letters, and each letter represents its own information, that is hexadecimal information, binary information, octal information, or any such information. Okay, so now again the next thing is numbers made of decimal digits. As you can see this particular number. Okay, so this particular number, both this non-decimal value and 0.32, this decimal value can also, that particular decimal value can also be represented in the pure decimals or pure binary values over there. Pure binary values, we can convert 239875 into binary first and 0.32 into also binary, and we can represent the complete thing in a discrete amounts of data in a digital system. Computers operate on binary values, that is 0 and 1, and it is easy to represent binary values electrically. Like if you are considering voltages and currents, can be implemented using circuits to create the building blocks of modern computers. So binary values can be used for any of these following purposes. So it will be very useful if we try to use the binary values, such as like if there is any low value, straight away I'll be assigning it to 0, and if it is a very high value, I'll be assigning it to 1. But that completely depends upon whether I have two type of two values are there, or 5 or 6 values are there. Like if there are 5 or 6 values, definitely I'll be using more binary formation. For example, like if I have 3, something like 7 are there. 7 values are there in a particular system. So what I'll try to do is I'll try to take 3 numbers to represent everything. That is, I'll take from 0, 0, 0 to 1, 1, 1 to represent these 7 values in between 0, 0, 0 to 1, 1, 1. That is 0, 0, 1, 0, 1, 0, 0, 0, sorry, 0, 1, 1. So on like that to 1, 1. Okay. So here it will be easier to represent it in the binary values rather than using the voltages and current values. So if you take the direct values in this one, we'll be getting this particular decimal values. Okay, which will be very cumbersome to do, to process anyway. Okay. So this is a basic organization of a digital computer. So first is, definitely the input has to be given to a particular system. The system can be consisting of anything. Here, for example, it is consisting of memory, control and arithmetic ALU unit. Basically, a CPU consists of all these units, that is memory unit, control unit and arithmetic logical unit. So once we get any particular data and instructions as an input, that input will be given to the memory. So for example, if I am going to multiply two numbers, 2 into 3. Okay. So now 2, 3 are data, and this multiplication is nothing but instruction. Okay. So this particular information is fed to the input block initially. Okay. Is fed to the input block. So now after feeding this particular information, that is data and corresponding instruction to the input, this will be saved in the memory. How it will be saved? Definitely, like directly. If I want to give 2 and 3, many times I can give it in the programming. But if I want to give in another way, what I need to do is here, I need to save this particular 2 value at particular memory location. Okay, 3 in particular memory location. Okay, and then after that, I need to perform some multiplication on this particular 2 locations over. These are nothing but the memory location. Memory location means like it will be having its own address, and I need to store it in a particular place. For example, this memory location is 0, 0. This is 0, 1. Okay. I need to store it in the particular memory location. Once it is stored, then I will be processing it. Okay. Directly, I won't be able to put it in the temporary memory and process it. So every time I need to store it in the memory. Then after that, what I'll do, I'll be trying to take into consideration. So what I'll give it, I'll give the data to the arithmetic unit, and also how to control the data. Okay, how to control the data, in what way I should manipulate this particular data, that is given to the control unit over here. That is the instruction, whichever is there, like multiplication operation. That multiplication operation here, whichever we consider right now. So that is given as a control over here, and data, which the numbers are 2, 3 are given to the arithmetic logical here. And once I get this information, I'll directly give it to the arithmetic block, and then I'll be getting some information, intermediate and final results. We'll be getting it back to the memory itself, and this memory location will be again differing. So once I give the values at 0, 0, 0, 1 location, the output might be stored at 1, 0 location here. Here the output might be stored initially. So once I store it, I'll be giving it to the output. So this is the way how the particular digital computer works. So whenever it takes some set of inputs, then it will be processing it by using, first it stores, then it processes using arithmetic logic unit and control unit. Then the final result will be given to the output, and this process will be continued. And here basically this lines are the intermediate signals, and these are nothing but the control signals. Okay, so directly we can get the output from the control signal, or indirectly I can get the information from the arithmetic, and here I can do the multiplication operation, and further again I can give it back to the arithmetic if it is not meeting. Okay, if further I have more and more instructions, again I have to come back, I have to take the information, again I have to move back here, and this process continues unless and until I get the final result. Okay, and sometimes here the result will be stopping at this point of time. Here the particular output will be getting, and directly that is stored in the memory and given to the output, and finally final result will be getting over here. So this is the way how the digital computer, like how the information processor in a particular digital computer. Okay, so next is here, before moving on to the number systems, okay, we should be able to know like systems, what are the different systems we have in a particular digital system technology. So now here we have different system that is with no state, like it doesn't require any state information in it. That is nothing but a combinational logic system. Okay, in the beginning we looked at the digital system block diagram, in which we will be giving discrete input and we get discrete output, and here some system is there, that is also discrete system. Okay, information processing system, and here I have some two arrows like this which shows the system state. Okay, so now every time there is no requirement of storing this particular system state. Okay, sometimes this system state is not required in some types of circuits. So for example, here we have combinational logic circuits. So it doesn't require any previous previous states in order to calculate the present state. That is to say, to calculate the present state, I don't require any past information. So that's why, like in such type of systems, there is no requirement of a state. That is, no state is present in such type of system. So now that is nothing but a combinational logic system. Okay, and the output is simply function of input. That is, whatever the changes are there in the output y, that will be the function of input simply. If x is the input, y is the output, it will be simply whatever the changes are done in the input, that will be directly reflected in the output with respect to the system function. Okay, that is first step. Next one, with state present. That is, first one without a state. Second one is the with state present. So what it will take into consideration is not only this particular y naught is y output, that is, it will take consideration into input as well as a state. The state information also it takes into consideration over here. So state updated at discrete times. That is, for example, once per clock tick. So if I draw something like this one, okay, this is a clock. Okay, that is on and off clock. Here it is 0, here it is 1, 0, 1, 0, 1. Okay, so whenever there is a clock tick, that is whenever a transition from 0 to 1 is there, I'll be getting an output. Okay, that is something like even from whenever it is moving from 1 to 0, or it has to be or only, because if I am considering clock ticks, then for every clock tick we should get the output. Or on the contrary, if I consider if it is if we are getting the output from whenever the clock is decreasing from 1 to 0, then for every time we need to consider only these things. Okay, clock negative tick, that is clock tick hash, like this we'll write in the code actually. Okay, so now here what we'll consider it is the state of the particular system as well as the clock state also, whether it is changing on. Even when I get some changes, okay, for example, here I have a time. Here this is a clock tick is it. This is a clock tick, this is a clock tick, this is a clock tick. Okay, so this is an analog signal or any other signal. Something is happening. Okay, if something happens in this period also, if there are any changes in the output in this period, that will not be reflected in the output. Okay, if there are any changes, like see if there is any change in this period or in this change in this particular period, okay, it will not be reflected unless that particular clock tick we are going to get. Okay, so that is nothing but it depends upon the state also. For example, it is a clock state also. Okay, so now in synchronous sequential system, state is basically updated at any time. Okay, so with respect to time, with respect to the clock, that particular state is updated and that state is taken into consideration. The other one is asynchronous sequential system. So in asynchronous sequential system, what we'll consider is there won't be any clock over here. Like even if the clock is there, that is for some other purpose. Here basically what we'll consider is the memory. Okay, what are the memory we store in the particular circuit, that will be taken into consideration. So if you look at the different types of systems in digital design, there will be systems without state and the systems with state present. Okay, these are the two things. Okay, so when the state is present, again it is divided into synchronous as well as the asynchronous over here. The information variation, okay, in any system is mapped to physical quantities. In digital systems, the quantities take on discrete values. That is, whether it is a 2-level or binary, values are the most prevalent values in digital systems. Binary values are represented abstractly by digits 0 and 1. So basically, whatever the information we have, it will be described in the physical in the physical form in terms of only 2-level information, that is a binary information, that is either 0 or 1 only. Okay, so now if you take any signal examples over time here, if we consider analog signal, it changes every time. See, as you can see the changes in the particular analog system here, analog signal. So you can see the changes are at every point of time. At every point of time, it is being changed. Even at this point also, even if there is no periodicity also, it is changing at this particular point, from this point to this point, this point to this point. So everything is being changed. Whereas when you move on to the digital system, that is digital asynchronous system, then you can see that change will be only at once. Okay, what it will take into consideration is here, if the value is very, very high, if the value is high, directly assign it into 1. If the value is low, assign it to 0 happily. So now as you can see this analog signal, here it is very low comparatively to these values. So directly we will be assigning it to 0 value. And now as soon as I get this one, I will be assigning it to 1. And again it moves to 0. Again it changes to 1 here till here. Again 0. Again 1. Okay, so if there won't be any other cases, we don't have any other values other than 0 and 1. If there won't be any 0.5, 0.2, 0.1, 1.1, 1.2, there won't be any other values other than 0 and 1. Okay, so we have to make sure that like whenever there is any digital signal, we'll be having either zeros or ones. So if you take into asynchronous system into consideration, then the changes will be abrupt, like with respect to the input, all the changes will be reflected in the asynchronous also. Now, let us consider for the synchronous system. So in the synchronous system, what's happening is here, whatever the changes occurs, it happens with respect to the clock. Here, these are nothing but the clock ticks. Clock ticks. Okay. If you consider this particular clock ticks here there is a clock tick. Okay. So now if you look at here, with respect to this one, we have a clock signal here. So initially it was 0. Again, at the clock tick, what is the value of the output is high. Okay. I'll change the value of output. Now, even if it moves to 0 also, we won't take into consideration. Rather than that, we'll wait for the another clock tick. I'll wait for another clock tick. So now, as soon as I get this clock tick, till here it will be 1 as usual. There won't be any change. As soon as I get any clock tick, I'll check for the value, whatever the value is. So here, how much it is? It is lesser value. So I'll give it to 0. So I have 0 here. Again, next time what I'll do? Again, I'll check for the clock itself. Okay, here the clock is there. Until here it will be 0 and again it changes to 1. Again it waits for the clock tick and again it changes to 0. So this process goes on. So in asynchronous, there won't be any problem with respect to any state, previous state, present state, like that. But the input next state will be depending upon the present state of the system. So that thing we need to consider in the Mealy-Murray machines. Whereas in synchronous system, in synchronous signals, what we have to consider is clock tick along with input. Okay, whatever the changes are there in the input, that has to be reflected in the output. But these changes will also depend upon the clock also. That is the state of the clock. So now coming on to the main number system. So basically, if you look at any digital system design, what we'll be coming across is different type of systems, that is decimal numbers, binary numbers, octal numbers, and hexadecimal numbers also. Majorly will be coming across this type of numbers. So the decimal numbers will be having the numbers from 0 to 9. That is, whatever the representation is there, we need to write in between 0 to 9 only. Okay, we should not use any other numbers. So you might be wondering, because most of the numbers will be coming from will be in range of 0 to 9 only. Why am I specifying like that? Because as I already said that in the number system we can use 26 alphabets also. Okay, 26 alphabets also. That is to say A, B, C. These things also can be used to represent the discrete information over there. So that's why this A value, B value, C value will also be having its own value in the digital system. Okay, so whichever the number you take, that has to be in between 0 and 9. So, but how many items does a decimal number represent? So, for example, if I take 8653 into consideration, here it has 8 into 10 to the power of 3 plus 6 into 10 to the power of 2, 5 into 10 to the power of 1 plus 3 into 10 to the power of 0. So, when you add all these things, you'll be getting a number. So, those many numbers, it will be representing it basically. Okay. So, if you take in the fractions into consideration, that is fractions means here I'll be getting 0.35 also, which is a rational number anyhow. So, here what I need to do is, after 4 into last number, this is last number, to 4 into 10 to the power of 0, I should consider 3 into 10 to the power of minus 1, 5 into 10 to the power of minus 2 also. So, this is a way to represent the particular decimal number. Okay. So, next comes the octal numbers. Octal, in the sense, octal word itself says that it has 8 digits over. So, when you consider the octal numbers, the range will be from 0 to 7 only. Okay, if you count all the numbers 0, 1, 2, 3, 4, 5, 6, 7, total will be 8 digits over there. So, now how many items does an octal number consider? Is here 4, 5, 3, 6. Same is the case. Instead of 10, you'll be having 8 here. So, 8 to the power of 3, 8 to the power of 2, 8 to the power of 1, 8 to the power of 0. And here you'll be getting 1, 3, 6, 2 to the base 10. So, this can also be considered as converting the particular octal number into a decimal number also. Okay. And if you consider the fractions, again the same way, 8 to the power of minus 1 and 8 to the power of minus 2. Once you add up all those things, you'll be getting to the base 10. And remember, the octal numbers don't use digits 8 and 9. So, whenever you get any 8 or 9 in a particular number, definitely that is not octal number. So, for example, I have a number 3, 4, 9, 2. Okay. If someone asks you what type of number it is, what type of number system, definitely it is not octal number, because it has a number 9 over here. Okay, even if it has number 8 also, it should not be considered as a octal number. So, as already repeated here, the octal number will be consisting of 0 to 7 only. In this particular, in any number, only 0 to 7 digits has to be considered. None other than these particular digits, none other than thing has to be considered over there. So, this is definitely not octal number. It can be decimal number. And binary numbers, we already know that it will be having only 0 and 1 values. So, how many items in the sense, like 1 into 2 to the power of 3, 0 into 2, 0 into 2 to the power of 2, next 1 into 2 to the power of 1, 1 into 2 to the power of 0. And you can write it as 11 to the base 10 also. So, again coming to the fractions, it will be into the 2 to the power of minus 1 into 2 to the power of minus 2. Once you add up everything, you will get in the terms of binary, decimal number again. Okay. So, now group of 8 bits is nothing but a byte. This thing we need to remember. 8 bits. Group of 8 bits is nothing but a byte. So, if we say 1 byte, then definitely it consists of 8 bits, 8 binary digits over there. Okay. And if we are considering any nibble, 4 digits will be there. That is 4 bits it will be consisting of. Okay. So, whenever we say a byte, then it has 8 digits or 8 binary digits over there. And 1 nibble is equals to 4 binary digits, as you can see over here. So, now Why to use these binary numbers? So as already discussed here, digital systems will be dealing with only mostly binary numbers only, that is either in zeros or ones. Okay. So now why to use this particular binary numbers? Okay. Same is explanation why we are going for digital system also. So now if you look at any particular this example of binary signals here, I'm saying it is 0 to 1, 3 to 4. Here there is some transition occurs between these particular two limits over here. So now if I have such type of transition, okay, instead of giving minute numbers, that is like here the numbers has to be 0, 1, 3, 4, like this I need to have, and in between also I'll be getting more numbers, 3.1, 3.2, 3.3, 3.4, like that I should have all the numbers. So instead of giving it like that, okay, it will be better if I assign all these lower numbers to 0 and all these higher numbers to 1. Okay, as you can see here, there is no change in this band. Like if you consider this complete band over here, there is no change. Like see, entire band is having its range to logic 1 only, and this entire band here, it ranges from 0, logic 0 only. So it's better to give a single value for that one, and whatever the transition occurs, we have to make it sure that it comes to the nearest one. Either it moves to the 1 logic or either it moves to the 0 logic. Okay, depending upon the whichever the technique we are going to use and whichever the application we are going to use, we have to make it sure that the transitions also should fall in the particular band of 1 or 0 only. Okay, so now why we need to use these binary numbers is it is easy to represent 0 and 1 using electrical values. Like if you are going to consider electrical values such as for voltages and currents, it will be easier to represent it in 0 and 1 rather than in decimals over. And these binary numbers has possible to tolerate noises. So here, how are they going to tolerate the noise? For example, I have a band of values here, just like here I told now. So 1.25, 1.253, like this. I have different values. So now, if there is any slight modification, in the circuit values because of tolerance levels or any other things like heating conditions or any, like if it is crossing some limit, okay, because of the tolerance will be something like plus or minus value only every time. We can't say ideally this is the value, but practically whenever we do that, because of different physical properties of that particular material, that there will be tolerance for each and every device over there. So this tolerance value will be varying from one point to the other point. From one time to the other time also it can be varying over there. So this tolerance value, okay, because it might be changing due to atmospheric conditions, temperature conditions, or any other noises which are induced into the system. So now if you are considering any normal system other than the binary system, the value will be 1.25, 1.253 in the next step. Okay, is there any change in this one? Just 0.003 change is there, and it's very very less comparatively. Okay, sometimes in other type of system, in analog circuits, it's very like we can even consider this change also, but most of the times this is a very negligible value. So what happens in this particular binary systems is, even if it changes to 3 also, it will be pointing it to directly straight away 1 or 0, or 0. Okay, there won't be any chance of interference of any type of noises into a particular system when we are using the binary numbers, and easy to transmit data. Definitely it's easier comparatively, like when we are considering all these set of values here, it will be cumbersome to it will be very difficult to send those particular values in the bytes format. Once we get this one, we need to convert it to another format, and it takes lot of space also to send all those numbers over there. So it will be easier to transmit the data if you are representing it only 0 and 1. Okay, and next, easy to build binary circuits also. As you can see, AND gate is one such binary circuit. As you can see, 1 and 0, that is 1 multiplied by 0. Like logic is A and B. Multiply 1 into 0, that is equals to 0. So It's easier to do this task also in the digital binary circuits if you are going to use the binary data rather than going for this particular real numbers or any other particular numbers. It will be easier to work on this particular binary data also. Okay. So now if I look at the particular conversion between number bases, I have decimal to binary I can convert, binary to decimal I can convert, binary to octal conversion we can do, and octal to binary conversion we can do, and binary to hexadecimal conversion we can do, and hexadecimal to binary conversion also we can do. So this is it for today's class, and in the next class we'll be discussing about how this conversion can be done from one number system to the other number system. That is how the base 10 system can be represented in base 2 or base 2 system vice versa here, and base 2 system can be represented in base 10 system, again base 2 to base 8 like this. Okay, whenever I say base 8 it is an octal system, and if I am saying base 8 we have to represent it in this way, that is some suffix we have to induce over it, like we had put it over there actually. So now again how to change from binary to octal, octal to binary, and again binary to hexadecimal, hexadecimal to binary. So all these things we'll be discussing in the next class. So to conclude this thing, today we have discussed about the overview of this digital system design course and the introduction to digital system design basic building block, that is digital circuit basic building block, which consists of a discrete input, discrete output, discrete information system, and also system states, how they are being changed. And next is a different type of digital systems, that is without any state information and with information of the state present, and that is asynchronous system and synchronous system. And next finally a basic introduction to the decimal, binary, octal systems over number systems over here. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.